Have you ever wondered how an artificial intelligence model sitting in a data center thousands of miles away can instantly generate a recipe for a cake, or how you can seamlessly stream a high-definition movie from across an ocean, when the vast majority of our planet is covered by dark, freezing, crushing water? This is Critical Path, where we explore stories and innovations about our global supply chain that connect our world to your everyday life. Let us start by addressing the elephant in the room, or rather, the cloud in the sky. The contemporary digital era operates under this grand, majestic illusion of absolute weightlessness. We use words like the cloud, Wi-Fi, and airdrop. We look up at the sky, at the invisible atmosphere, and we just assume our emails, our financial transactions, and our late-night impulse purchases are floating around up there in the ether, beamed down from satellites by the tech gods. It is a pervasive sense of ethereal connectivity that makes us feel like we are living in the world of Star Trek. However, I am here to completely ruin that illusion for you. The technical reality of our modern, hyper-connected world is incredibly grounded. Or, to be more accurate, it is entirely submerged. Prepare yourself for a statistic that might hurt your brain. Approximately 99% of all transoceanic data traffic is not transmitted via satellites or magical wireless signals. No, 99% of it travels through a fragile, physical network of fiber-optic cables resting on the freezing, high-pressure, mud-covered floor of the world's oceans. That is right, we are not a wireless world at all. We are a world that has simply learned to hide its wires very, very well. The seamless, instant streaming of a video on your handheld device relies entirely on a physical, wet hose sitting in the dark of the ocean floor, positioned right next to shipwrecks and giant squids. The cloud is not in the sky. The cloud is a series of pressurized tubes under the waves. We have built an advanced, weightless, high-tech civilization on a foundation of what is essentially Victorian-era plumbing. This invisible supply chain is one of the most complex, specialized, and downright absurd industrial endeavors in human history. To connect hyperscale data centers across continents, humanity has deployed over 1.4 million kilometers of submarine telecommunications cables. Let me repeat that. 1.4 million kilometers. That is a distance equivalent to circling the entire Earth more than 35 times. And these cables, which constitute the literal nervous system of the global economy, are often no thicker than a common garden hose in the deep sea. They exist in a state of constant, terrifying peril, vulnerable to everything from tectonic shifts to a careless guy named Gary dropping a heavy piece of metal from a boat. The story of these deep-sea veins is an epic saga. It is a journey that starts in ultra-sterile manufacturing plants where glass is cooked like a gourmet meal, moves to the decks of a highly niche fleet of ships, of which there are fewer than 60 in operation worldwide, and ends in the deepest, darkest trenches of the ocean. So how do you actually make the physical internet? The culinary chemistry of connectivity begins in an environment that looks less like a dirty factory and much more like a high-end, futuristic laboratory. The absolute core of the modern internet is silica glass, but this is not the glass of your living room windows or your water glasses. This is silica glass of such extreme purity that it defies human imagination. Even the slightest microscopic contamination can result in a catastrophic loss of signal. The manufacturing process is a wild, multi-step orchestration of chemical vapor deposition, extreme heat, and gravity. It begins with something called preform manufacturing, typically utilizing a method called modified chemical vapor deposition, or outside vapor deposition. In the modified chemical vapor deposition process, gases are heated inside a rotating silica tube, which allows the core and cladding materials to be deposited in layers with absurdly high precision. To get the necessary optical performance, manufacturers use silica that has a purity level of 99.999%. This 99.99% purity is not just a marketing gimmick or a preference for high quality, it is a strict physical requirement. You are dealing with a medium that is intended to carry light for thousands of kilometers, with minimal attenuation. We are talking about attenuation rates as ridiculously low as 0.18 to 0.19 decibels per kilometer. In this environment, even a single microscopic particle of dust could act as a massive brick wall crashing into your data pulses. Once this deposition process is complete, the preform is sintered at temperatures between 1600 degrees Celsius and 1800 degrees Celsius. This mind-boggling high-temperature treatment eliminates any remaining air bubbles to achieve the unmatched optical clarity required to send your emails across the Atlantic Ocean. The result of this baking process is a solid, transparent rod of glass that serves as the blueprint for the final fiber. But a solid rod of glass is not a cable. You have to stretch it. The transition from a solid rod to a hair-thin fiber occurs in something called a drawing tower. This is a massive vertical structure that can be several stories high. The tip of the glass preform is heated in a furnace to a temperature of approximately 2000 degrees Celsius to 2200 degrees Celsius, causing the silica to soften into a molten state. Then, they simply let gravity do the work. Gravity pulls the melted silica downward, forming a microscopic thin strand of fiber. This drawing process requires constant, millisecond-level monitoring. A laser system measures the diameter of the descending fiber as it falls to ensure it remains exactly 125 microns thick. To put that in perspective, that is roughly the size of a human hair. And the tolerance for error, a mere plus or minus 1 micron. Before this hair-thin glass is even fully cooled from its 2000-degree melting point, a completely unpronounceable ultraviolet-cured polymer coating is rapidly applied. This coating is absolutely critical. Without it, the fiber would develop microscopic surface cracks the literal second it made contact with the air, which would significantly reduce its tensile strength and its optical life. So now we have the star of the show, the incredibly pure, hair-thin glass fiber. But while the fiber is a miracle of science, it is physically helpless against the brutal environment of the deep sea. If you dropped a bare fiber into the ocean, it would be crushed instantly by the pressure, or snapped in half by a passing crab. Consequently, the manufacturing process has to envelop these fiber bundles in multiple layers of heavy-duty protective materials. The specific architecture of a submarine cable is an absolute masterpiece of material science, perfectly designed to balance flexibility, strength, and durability. It is like dressing a strand of spaghetti in a suit of Iron Man armor. Let us look at the anatomy of this armor, layer by layer, going from the outside in. Layer number 1 is the outer jacket, made of polyethylene, acting as the ultimate waterproofing and environmental protection raincoat. Layer number 2 is mylar tape made of polyester resin, providing a moisture barrier and internal insulation. Layer number 3 brings the heavy metal, stranded steel armor wires for serious tensile strength and mechanical protection against anything trying to cut it. Layer number 4 is a water barrier made of solid aluminum, designed to prevent water and hydrogen ingress. Layer number 5 is an internal support structure made of polycarbonate for structural rigidity. Layer number 6 is the conductor, made of copper or aluminum, which conducts direct current power to the repeaters, which we will talk about later. Layer number 7 is filler, and you will love this. It is made of petroleum jelly or paraffin. Yes, your high-speed global internet is quite literally slathered in petroleum jelly to cushion the fibers and block water. Finally, sitting in the very center is layer number 8, the optical core, made of those high-purity glass fibers, acting as the actual data transmission medium. The resulting cable varies in thickness depending on its destination. In the deep-sea sections of the abyssal plain, where there is virtually zero human activity and nothing but creepy deep-sea fish, the cable is surprisingly thin. It is often only 17 to 20 millimeters in diameter, roughly the exact size of a standard garden hose. However, as the cable approaches the continental shelf and the shoreline, where the risk of ship anchors and fishing nets increases exponentially, it gets a massive upgrade. It is reinforced with heavy steel armoring, often becoming several times thicker and much heavier. So, you have manufactured the cable, now you have to transport it and lay it across thousands of miles of unpredictable, violent ocean. This monumental task falls to one of the rarest, most highly specialized types of vessels on the entire planet, the cable-laying ship. As of early 2024, the entire global fleet of large, specialized cable-laying ships is estimated to consist of only about 60 units. Let me say that again, 60 ships, for the entire planet. This extreme scarcity creates a massive, glaring logistical bottleneck in the global internet supply chain. If the internet breaks, the world cannot simply call a local plumber. We rely on a handful of ships that are rarer than billionaires. These cable-laying ships, such as the René Descartes operated by Orange Marine, are not just boats. They are essentially massive, self-contained floating factories. The heart of these ships consists of enormous, circular, cavernous tanks where the cable is coiled. A single ship can carry over 2,000 kilometers of cable, weighing thousands upon thousands of tons. The loading process itself is a mind-numbing feat of patience. The cable is hauled directly from the manufacturing factory and coiled by hand into the ship's tanks to prevent tangling and to ensure a perfectly smooth deployment. Imagine trying to coil a garden hose that is 1,000 miles long without a single kink. For just a 1,000-kilometer section of cable, the loading process can take a full week of continuous, 24-hour operation. The economics of this vessel scarcity are fascinating and terrifying. The market for these ships is defined by astronomical capital costs and extreme global demand. A state-of-the-art cable-laying ship can cost several $100 million to build. Furthermore, the global rise of offshore wind farms has created a massive secondary demand for these exact same ships to lay power cables instead of internet cables, further straining the availability for telecommunications projects. The global market size is forecasted to grow from $761.81 million to a staggering $1.95 billion by 2034, growing at an annual rate of 11.03%. In 2024 alone, approximately 40% of new orders were focused on power and wind cables, leading to a charter contract delay rate of around 18%. Because of this intense scarcity, repair ships have to be strategically stationed at key global ports, such as those in the Atlantic and the Mediterranean. They sit there, fully crewed, waiting on 24-hour standby for a disaster call that could come at any given moment. Now, let us talk about landscaping the abyss. Laying a cable is not as simple as dropping a heavy rope over the side of a moving boat and hoping for the best. It is a highly coordinated, incredibly stressful engineering operation that begins years before the ship ever leaves the safety of the harbor. The very first step is a meticulous marine route survey. Engineers use high-tech multi-beam echo sounders and side-scan sonar to map the underwater topography in ultra-high resolution. They are essentially playing a giant video game, looking for the most stable and hazardous-free path. They have to carefully route the cable to avoid underwater volcanoes, steep treacherous trenches, and areas prone to seismic activity or massive underwater landslides. But nature is not the only obstacle. They also face a far more terrifying human obstacle: unexploded ordnance. In areas like the Baltic Sea or the North Sea, the seabed is literally littered with explosive remnants of past world wars. Before a single inch of cable can be laid, high-resolution geophysical surveys and video inspections are conducted to specifically identify and carefully avoid these spicy installation challenges. Immediately before the actual cable is deployed, the ship performs what is known as a pre-lay grapnel run. This sounds like a maritime extreme sport, and it kind of is. The vessel drags a giant, multi-hooked anchor called the grapnel along the exact planned route to clear away all the garbage humans have left behind. They are dragging the bottom to snag ghost fishing nets, abandoned ropes, and old, out-of-service cables. This ensures that when the massive, expensive cable plow is finally deployed, it does not get snagged on random debris that could damage the multi-million-dollar equipment or snap the brand-new cable itself. Wait, did I say cable plow? Yes, I did. In shallow waters, which typically means anything up to 1,000 meters deep, the cable is not simply laid nicely on the surface of the mud, it is buried. To achieve this, the ship tows a massive, terrifying underwater cable plow that can weigh upwards of 50 tons. The delicate glass cable is fed through the plow's internal mechanism. As the 50-ton plow is dragged across the ocean floor, it lifts a giant wedge of sediment, allowing the cable to be safely inserted underneath. The displaced sand and mud then naturally settles back over the cable, providing a beautiful natural armor against the very things that want to destroy it: ship anchors and fishing trawls. In even more highly sensitive areas, such as when the cable makes its shore approach right up to the beach, engineers use jetted systems or vertical injection tools. These incredible devices use high-pressure water jets to literally fluidize the solid seabed, turning the dirt into soup, allowing the cable to effortlessly sink to depths of several meters before the sand or mud resettles and traps it safely in place. Now here is one of the most surprising, wildly counterintuitive aspects of a submarine data cable. It is not just carrying internet data. It is also a massive high-voltage power line. You see, light signals traveling through fiber-optic glass eventually fade out due to attenuation, which is just the loss of signal strength over distance. The light simply gets tired. To cross an ocean, these fragile light signals must be artificially boosted every 60 to 100 kilometers. The devices that perform this critical boosting are called repeaters. Modern repeaters are marvels of engineering. They utilize something called erbium-doped fiber amplifiers. This technology uses a solid-state laser to physically excite a specific section of the fiber that has been chemically infused with erbium ions. As your weakening data signal, carrying that funny cat video, passes through this highly energized segment of glass, it is magically amplified without ever needing to convert the light back into a clunky electrical signal. This brilliant process allows for massive data throughput using a technique called wavelength division multiplexing, which can carry millions of simultaneous phone calls or high-definition video streams on a single, tiny pair of fibers. But here is the catch. How do you power a highly sophisticated laser amplifier sitting at the bottom of the ocean, thousands of miles from the nearest electrical outlet? To power these submerged repeaters, which must operate flawlessly for a design life of 25 years with absolutely zero maintenance, at crushing depths of up to 10,000 meters, a constant, massive direct current is pumped straight through the cable's inner metallic conductor layer. Power feeding equipment located at the landing stations on the shore generates terrifying voltages that can reach anywhere from 3,000 to 15,000, or even upwards of 18,000 volts of direct current. They are pumping between 1.0 and 1.6 amps of current, with a total power input of up to 16.5 kilowatts, straight into the ocean. And the electrical circuit is completed in a way that sounds like absolute madness. The return path for all of this electricity is the earth and the sea itself. By grounding the system at both ends of the ocean, the literal ocean water becomes a giant, planetary-scale conductor, closing the electrical loop and allowing the data-carrying light to travel across the planet safely. It is both brilliant and terrifying. However, despite the 8 layers of armor, the 50-ton underwater plows, and the brilliant engineering, the world's digital lifelines are shockingly, laughably fragile. Approximately 200 cable faults occur globally every single year. That is nearly 4 massive internet breaks per week. While natural disasters like underwater landslides or random earthquakes account for about 12% of these faults, the vast majority are caused by a much more chaotic force: human activity. The primary, ultimate villain in the story of global cable disruption is the ship's anchor. An anchor dragged by a vessel underway can cause catastrophic, continent-wide damage across a massive area. You might think dropping an anchor is a precise action, but in the maritime world, mistakes happen that border on the comedic. One of the most significant events in recent history occurred off the beautiful coast of Sicily in 2008. A ship somehow accidentally dropped its anchor and proceeded to drag it along the ocean floor for a mind-bending 300 kilometers. 300 kilometers! In the process, this rogue anchor damaged 6 different major submarine cables and caused a widespread, devastating internet blackout across multiple entire countries. Another incredible incident took place in the Great Lakes of Michigan. A ship managed to drag its anchor for an unbelievable 36 hours straight, covering over 600 kilometers of ground, completely oblivious to the destruction below. It damaged 5 different cables and multiple underwater pipelines. These are not just tiny funny oops moments, they are multi-million-dollar logistical nightmares that paralyze global communication. A single deep-sea cable repair can cost anywhere between $500,000 and $1 million, depending heavily on the depth and the remote location. When a massive steel anchor slices through the internet, the repair process is an intricate, highly stressful microscopic surgery performed from a swaying ship on the surface of a stormy ocean. First, they have to find the break. Technicians use a brilliant technology called time-domain reflectometry. They essentially shoot a pulse of light down the broken cable from the shore and carefully measure the exact time it takes for the reflection from the break to bounce back. This math allows them to locate the damage to within 1% of the cable's entire length. Then comes the hook and the slice. A specialized repair ship travels to the exact site and begins dragging a massive cutting grapnel perpendicular to the broken cable on the seafloor. This brutal tool snags the damaged cable and literally severs it in half, dropping both cleanly cut ends back to the seafloor. Next comes hauling it to the surface. The ship deploys a recovery grapnel to hook one of the ends and physically haul it thousands of feet up to the surface, where it is secured and buoyed off so it doesn't sink again. They then repeat the exact same tedious process for the other end of the cable. Once both ends are on the ship, the real magic happens in the jointing shop. Inside a specialized, highly controlled cleanroom located right on the ship's rocking deck, technicians meticulously strip away the heavy steel armor and expose the hair-thin glass fibers inside. They then use an incredibly precise device called a fusion splicer to literally melt the tiny glass ends together with an electric arc, creating a bond that is both physically strong and optically flawless. After rigorous testing, this freshly repaired section is sealed inside a joint body, which is a heavy-duty, high-pressure casing that provides mechanical strength and waterproofing. The entire assembly is finally lowered gently back to the seabed. Because they had to pull extra slack up to the surface to perform the surgery, the final result is a repair bite on the sea floor, which is a slight, intentional loop in the cable that ensures the minimum bend radius of the fragile fiber is strictly maintained. Now, before we move on to modern warfare, I need to address the most enduring, hilarious myth in the entire submarine cable world, the myth that sharks are a major threat to the global internet. We have all seen that one viral video of a shark viciously biting a cable, making global headlines and causing everyone to panic. However, historical data proves that fish bites are incredibly, vanishingly rare. Between the years 1901 and 1957, at least 28 telegraph cables were indeed damaged by fish, but that number plummeted dramatically as cable designs improved. And from 2008 to 2013, exactly 0 cable faults were attributed to sharks. The original shark attack events that occurred in the 1980s off the Canary Islands were actually attributed to deep-dwelling crocodile sharks, which were likely attracted to the strange electromagnetic fields of early lightwave systems. Modern cables now conveniently include an extra, specific layer of fish bite protection, just to prevent these extremely rare underwater curiosities from becoming massive global outages. So no, Jaws is not eating your Wi-Fi. But in the 21st century, the vulnerability of submarine cables has taken on a significantly more sinister, terrifying dimension. National security officials are increasingly concerned that what look like accidental, clumsy anchor drags by tired ship captains may actually be highly coordinated, deliberate acts of international sabotage. Let us look at the geopolitical grey zone. In November of 2024, 2 absolutely critical cables located in the Baltic Sea, the Sea Lion 1 and the BCS East-West Interlink, were cleanly severed within mere hours of each other. The international investigation quickly focused on the Yipeng 3, a Chinese cargo ship that just happened to be loitering in the exact vicinity. Subsequent drone images later revealed the ship sporting a heavily mangled anchor. Investigators strongly suspected the crew had intentionally dropped the anchor, while the ship's massive engines were still propelling the vessel forward, effectively using their boat as a giant underwater plow to tear through the seabed for 160 kilometers specifically to cut the lines. A chillingly similar alarm was triggered just a month later, on Christmas Day, 2024. The Eagle S, a Russian Shadow Fleet oil tanker, raked its heavy anchor violently across the Estlink 2 cable off the freezing coast of Finland. In a dramatic escalation, Finnish special forces actually boarded the ship. This was the first such military seizure of its kind since World War II. They boarded after the Russian crew confidently claimed their anchors were up and completely secure, when they were quite clearly dragging them across the ocean floor. Investigators easily found a massive, continuous 66-mile drag mark dug into the mud leading directly to the Russian ship. Other notable incidents include the Aconcagua in 2002, which cut 3 of 4 major transatlantic cables. The Blue Princess in 2012, which severed 3 major systems in the Red Sea in just 12 hours. And the Rubimar in 2024, whose drifting anchor cut 3 cables after suffering a direct missile strike. These terrifying incidents heavily highlight how a relatively low-tech, ancient tool, like a rusted iron anchor, can be effectively weaponized as a high-impact tool of modern hybrid warfare, directly threatening the digital sovereignty and economy of entire nations. Because of these massive physical vulnerabilities, the ownership of the ocean is rapidly changing. Historically, submarine cables were strictly the boring domain of national telecommunications carriers and old-school phone companies. However, the last decade has witnessed a massive, fundamental transformation in the industry's entire ownership structure. Poseidon has new masters, and they are the web-scale tech companies. The arrival of hyperscalers, namely Amazon, Google, Meta, and Microsoft, has completely reshaped the map of the ocean floor. These massive tech giants now represent more than 70% of the overall global submarine cable market. Their logic for buying up the ocean is purely operational. To support the truly massive data loads required by modern artificial intelligence training, global cloud services, and endless social media scrolling, they desperately need to reduce their reliance on slow, third-party telecommunications providers. By building and owning their own massive private cable networks, they gain ultimate control over 3 crucial factors. First is latency. They want to ensure the absolutely fastest possible route between their massive global data centers, of which over 1,189 are currently active worldwide. Second is redundancy. They are actively building self-healing rings of cables, ensuring that if one cable is violently severed by a Russian anchor, your data can be instantly rerouted around the globe without you ever noticing a buffer screen. Third is security. They are completely integrating military-grade encryption and trust architectures directly into the physical cable system design itself. This massive shift has hyper-accelerated cable technology innovation, pushing data throughput from traditional 20 to 40 terabits per second systems all the way to mind-bending new 400 terabits per second class designs. They achieve this using advanced technologies like space division multiplexing and highly advanced coherent optics. But perhaps the most exciting, mind-blowing development in all of subsea infrastructure is the recent realization that these dumb glass tubes can do significantly more than just transmit your emails. They can actually sense the physical world around them. By ingeniously repurposing existing telecommunication fibers using a technology called distributed acoustic sensing, or DAS, brilliant engineers are effectively turning thousands of kilometers of standard cable into massive, continuous, planetary-scale sensor arrays. Distributed acoustic sensing relies on a physical phenomenon known as Rayleigh scattering. As light pulses travel down the glass fiber, microscopic impurities in the glass naturally reflect a very tiny portion of the light signal back to the source. When a loud sound or physical vibration hits the outside of the cable, it causes a microscopic strain in the fiber that subtly changes the phase of that reflected light. This basically turns the cable into the world's longest microphone. This technology allows a single submarine cable to provide continuous, high-resolution monitoring of seismic activity over 100 kilometers or more stretching from the shore. It can be used as a global early warning system. It can precisely detect tsunamis and massive earthquakes, sensing dangerous tremors thousands of kilometers away with incredible precision. It can physically track moving ships by identifying the unique acoustic signatures of vessels above, including exact propeller rhythms and heavy machinery noise. This specific capability allows for the real-time monitoring of dark ships that have intentionally turned off their public tracking systems to hide their locations. Most importantly, it can protect the infrastructure itself by instantly detecting the terrifying vibration of a ship's heavy anchor dropping through the water before it even hits the cable, potentially allowing port authorities to take preventative action before the internet goes completely dark. This innovation beautifully turns the fragile supply chain of the internet into a proactive, intelligent shield for the world's oceans, providing a level of spatio-temporal resolution that traditional underwater hydrophones simply cannot match. To truly appreciate the sheer madness of this engineering, one must deeply understand the crushing, hostile reality of the deep-sea environment where these cables live. The ocean floor is a place of absolute extremes that would violently destroy almost all human technology. Let us talk about the physics of depth. The physical pressure in the ocean increases by 1 atmosphere, which is approximately 14.69 pounds per square inch, for every single 10 meters of depth you descend. At the average ocean depth of 3,800 meters, the pressure is roughly 380 times greater than the pressure you feel on the surface. But in the deepest hadal-pelagic zones and hadal trenches, which can reach depths of 11,000 meters, the pressure is a mind-boggling 1,100 times greater than sea level. To quote the research, that level of pressure is essentially measured in elephants per human thumb. The temperature down at these terrifying depths, specifically in the abyssopelagic and hadal-pelagic zones below 4,000 meters, hovers just marginally above freezing, typically around 4 degrees Celsius or 39 degrees Fahrenheit. There is absolutely zero light. It is pitch black. Ironically, this utterly freezing environment actually aids the technology, as the frigid water provides a constant, highly effective, passive cooling system for those high-voltage repeaters that would otherwise rapidly overheat and melt. As we peel back the many layers of the global internet, from the polyethylene jackets to the erbium-doped lasers, we arrive at a startling, profoundly counterintuitive realization. It is an aha moment that completely shifts how you will forever view our so-called wireless world. The magical, seamless, instant streaming of a movie on a shiny new smartphone relies entirely on a physical, mud-covered cable sitting in the freezing, high-pressure, pitch-black dark of the ocean floor, positioned precisely within the physical reach of a 20-ton iron anchor, casually dropped by a rusty freighter built in the 1990s. We proudly live in an age where we can talk to artificial intelligence in real time, yet that entire interaction is physically tethered to a literal hose lying next to ancient shipwrecks in the mud. This high-tech civilization is built entirely upon a foundation of Victorian-era plumbing concepts. It is a physical network so shockingly vulnerable that a single tired ship captain can accidentally unplug an entire sovereign country while simply trying to park his boat during a minor storm. The grand realization is recognizing this inherent fragility. Our most advanced, weightless, ethereal digital experiences are completely, permanently anchored to the most ancient, brutal, and unforgiving realities of the deep sea. We are not a wireless world. We are a world entirely dependent on very long, incredibly brave wires. We have learned that the entire global internet is bravely supported by a tiny, niche fleet of only 60 specialized ships, each carrying thousands of kilometers of fragile glass, operating with a stressful 25-year zero-maintenance mandate. We have seen how terrifying high-voltage direct current power uses the entire ocean as a return path to keep tiny light signals alive through erbium-doped amplifiers. We have also uncovered the absolute logistical nightmare of deep-sea cable repairs, where highly trained technicians must perform microscopic fiber surgery on a violently swaying ship's deck, while buoying off multi-ton cable ends over an abyss. Yet, the core problem fiercely remains. The external aggression of human activity, ranging from legitimate fishing accidents to suspected international sabotage, continues to be the leading cause of massive cable faults globally. The brilliant emergence of distributed acoustic sensing offers a genuine glimmer of hope, potentially turning these completely passive cables into active, listening sentinels that can actually hear a threat before it physically strikes. As megacorporations like Google and Meta continue to invest countless billions into these proprietary deep-sea veins, the map of the world continues to dramatically change beneath the waves. But even with the absolute most advanced artificial intelligence and the purest glass humanity can forge, the world remains entirely hardwired. Every single byte of data we send across the ocean is a beautiful testament to the incredible, invisible, and surprisingly fragile physical link sitting quietly in the freezing dark of the ocean floor. Keep that in mind the absolute next time you quickly stream a movie or send a text message overseas. It is not satellite magic, it is a very long, incredibly impressive piece of glass. Now, I want to hear your thoughts on this incredible hidden world. If a rogue cargo ship anchor suddenly cut your country's internet access for a full week, what is the very first thing you would do to survive the digital blackout? Let us know down in the comments below. Thanks for listening and watching. Please like and subscribe, and make sure to check out our other videos about the global supply chain.